So we're introducing another kind of significance test when you're dealing with categorical data and some counts around those. Very much they're like regular significance tests, but we're going to have to be dealing with a slightly different test statistic and a different distribution. This first section deals with the chi-square goodness of fit test, which allows us to compare what we expect from a distribution of categorical variables and what actually happens and see if it's statistically significantly different. We can decide whether a distribution of categorical variables differs for two or more populations or treatments. So when we're analyzing an experiment where you have more than one treatment, we need a chi-square test for homogeneity. And we will often organize our data in two-way tables. And remember, we looked at independence previously in the year during the probability unit, but the chi-square test of independence allows us to decide if there's convincing evidence of an association between variables in the population at large, and see if it's just by random chance or if it's possible that there is an actual association. Looking at the example that we used in class, just to clarify how a one-way table looks, we've got our categories and we've got our counts for each category. It's like a visual bar graph without the actual colors or the bars. In this particular case, it talks about the outcome when 60 M&M candies were looked at. So we can look at one sample proportion, and we can compare the blues in what is expected, and then blues in what happened in our sample, and we can compare those with a one sample z-test. That the hypothesized value is 24% because that's what the company said, and then that it's not 24%. And we can perform that one sample z-test for each proportion, but that's going to be inefficient, and it could lead to the problem of multiple comparisons where we have so many opportunities to get a type 1 error that it's really not very accurate. So we have to have a different method when we're looking at categorical data. So as I said, we don't want to take that one sample z-test for each color. It wouldn't tell us how likely it is that we would get a random sample of 60 candies with a color distribution that differs. So we have a new kind of significance test called the chi-square goodness of fit test. And it just basically says how far apart are the distributions between what we expect and what actually happens, or so expected minus observed minus expected. So just like all significance tests, we're going to start with a null and an alternative hypothesis. In this case, our null is that the company's stated color distribution is correct, and that's the percentages that the company has said are true about each of the colors. And then the alternative hypothesis is that it doesn't work. So we'd have a does not equals if we were writing it in symbols, and we have. So we can also write the null and the alternative using symbols, where we delineate the distribution that's accepted, and then talk about the fact that the alternative, at least one of the probabilities, is incorrect. And then P sub color is the true proportion, population proportion of M&Ms of that color. The idea of a chi-square goodness of fit test is this: we are comparing the observed counts from our sample with the counts that we would expect if the null is true. Just like all significance tests, our null builds the distribution, and we're checking how rare it is that the alternative value from our sample happens just by chance. And if it's a small occurrence, then we're going to reject the null. The more the observed counts differ from the expected counts, the more evidence we have against the null hypothesis. So a high chi-square statistic is better evidence against the null. So we're assuming that the color distribution stated by Mars is true, because that's what we've decided our null is. Then 24% of all the M&M milk chocolate candies are produced are blue. So we would go ahead for our expected. We would take 24% of 60, because we're doing a random sample of 60. And notice that we've left this to the 100th place. That's our expected count of blue M&Ms. And we continue this method for all 6 categories, finding the expected counts. We're going to use observed minus expected squared, and then divide by the expected to find our chi-square statistic. So when you notice that there's differences between the observed and the expected, in this case the expected is red and the observed is purple, shall we say, you'll notice that sometimes the expected is a lot higher than the observed and vice versa. So just like with standard deviation, we take the difference and square them to offset the ones that are above and below from canceling each other out. We do the same thing with a chi-square statistic. So we're going to the observed minus the expected squared, and then we divide by the expected, because some things are expected more frequently, and so we have to weight those things appropriately. So you're going to look at, this is very similar to the expected value that we deal with in random variables. So you're going to take the observed minus the expected squared, divide by the expected, then you're going to add them all up, and that is your chi-square statistic. So here we have a step-by-step of the, and color-coded for those of you who like color-coded. So basically you're taking your observed minus your expected, square it, and divide by the expected. So, and then you continue to do that for all of the different categories, add them all up, and you get your chi-square statistic. Here, in this case, it's 10.180. And chi-squared is the distance of the observed count from the expected. Similarly, as I said, the way that we look at standard deviation being the distance from the mean. Larger values of chi-squared, because it's the sum of all of them, are stronger evidence against the null, because they say that the observed counts are farther away than we would expect. Small values suggest the data are consistent. But because if you're comparing two things, yeah, you can compare the larger and the smaller, because the expected and observed might be different in a lot of different situations. We still continue to go and use our distributions and a p-value to allow us to make decisions. So chi-square distributions are different than t-distributions and normal distributions. Since chi-squared can never be negative, they're always going to be distributions that are skewed right. They're always going to only be in the first quadrant, positive, and their degrees of freedom is always going to be where we find which distribution to look at. And the degrees of freedom is the number of categories minus 1. I don't know why chi is not coming out here. That's all I need to say there. We're never really going to be graphing them ourselves. There's some interesting components to them. The mode is always going to be you don't have to know this, but for any time you have a degrees of freedom greater than 2, the mode is going to be at 2 less than degrees of freedom, and the mean is equal to the degrees of freedom, just for, knowledge. We read a chi-square distribution table very similarly to the way we do a t-distribution table, where you find your p-value and you find your degrees of freedom, and then if that value is somewhere in the middle, you're going to look at this tail probability up top, and in this case it falls in between 0.10 and 0.05. So if we're using a standard alpha of 0.05, we would not reject the null here. We don't have sufficient evidence to conclude that the company's claimed color distribution is incorrect. So once again, our chi is always going to be this skewed to the right thing. It's always going to be positive because the squared part of the chi. Conditions are similar to the conditions we've been using for all of our significance tests and confidence intervals. If it's not random, throw it out. If you are sampling without replacement, go ahead and make sure that it's less than 10% of the total. In this case, large counts has to be looked in terms of the expected counts. And you can't use the proportion that you are given, but you have to multiply that proportion by the sample size, because you're already going to have what happened in each sample, but you have to multiply by the proportion expected times the sample size, so you know to be able to compare those two. Make sure you're using expected counts in that large counts and not the observed ones. Blah, blah. So this is the whole thing in one place, and I don't think you need me to read it for you. But basically, oops, except once again, it doesn't read the chi. Here we go. Whoop, and there we go. You can read this to yourself. It's the same process, just make sure you realize how the things are different. And I'm going to run you through a real quick one here. In his book Outliers, Malcolm Gladwell suggests that hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Since January 1 is the cutoff date for youth leagues in Canada, where many National Hockey League players come from, players born in January will be competing against players up to 12 months younger. So the older players tend to be bigger, stronger, more coordinated, and then will have a better chance of getting playing time, coaching, and being successful, and therefore making the NFL. So to see if the birth date is related to success, birth date is a category. We look at a random sample of 80 National Hockey League players from a recent season and look at their birthdays. It's broken down into 4 categories: January through March, April through June, July through September, and October to December. If there was no if our assumption is that the birthdays are evenly distributed. That's our null hypothesis, that there will be, of the 80, there should be 20 in each of the breakdowns. And the alternative hypothesis is that they're not evenly distributed. Now, we know what the researcher thinks is happening is that the people born earlier in the year have a better chance. And so we're going to go see if that distribution plays out. The data came from a random sample. It's 10% because there are 879 NHL players, and the 80 that were chosen is less than that 10%. And if the birthdays were evenly distributed, as I said earlier, then we would end up with 20 in each category, which is more than 5. So the expected counts meets, the large counts is met with that expected count being more than 5. So here the test statistic for our chi-square test statistic is for January through March, for example. There's 32 people with that birthday minus the 20 that was expected, squared, divided by 20, et cetera, et cetera, et cetera. We add all 4 of the categories of the months, and we end up with a chi-square statistic of 11.2. That seems kind of high, but once again, we're going to fit it by looking at a chi-squared distribution with the degrees of freedom of 3, because there's 4 categories. 4 minus 1 is 3. Then we go ahead and go to the degrees of freedom of 3, and here is our 11.2, somewhere here in this middle of this. So our p-value is between 0.02 and 0.01, and we decided we were going to work with an alpha of 0.05. So because our p-value of 0.011, that would be a super specific that was probably gotten from a calculator and not the table, or we can just say because a p-value is between 0.01 and 0.02, and it's less than 0.5, we reject the null. We do have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year, which gives some evidence to the author's hypothesis that early birth year gives you a better chance of getting into the NHL. Chi-square significance tests are run the same way as the rest of the significant tests. We have hypotheses, null and alternative. We have a test statistic. In this case, it's taken from the difference of the observed minus expected count squared divided by expected counts, degrees of freedom. Chi-square distributions are all positive, but we still look at degrees of freedom, 1 minus the number of category. We find the p-value in the table or using our calculator and use the p-value less than the alpha, reject. P-value more than alpha, fail to reject. If we do reject, we will look back at the original information to decide what part of categories or what categories really pushed in the direction of statistically significant, because that information is going to tell us something.